Thank you for coming to my dissertation defense. I will talk about my work as a graduate student here. It's basically the training to how to model complex biological phenomena into mathematical model and hence solve them computationally. So first let me give you the outline of my talk. So first, the basic modeling part, the biological phenomena we model here is the cell signaling model. How two cells interact between each other. That's the and what is the mathematics behind that phenomena. And first, we need to present some background and motivation that why this problem is important and why we find this problem interesting, and what is the mathematics behind this to capture the whole situation. And we'll present two kind of model. One is the sequential phosphorylation model, and our model is different than the traditional model because we introduce some special component into our model. It's called scaffold protein. And first we'll discuss the sequential phosphorylation. Then we'll discuss more complicated cascade model, like layer-wise model, and again we'll introduce scaffold protein into that model. Then we'll summarize the whole realization of our finding. Then the second part of my training is how to design some effective scheme to solve reaction diffusion advection system. Reaction diffusion advection system are very important and frequently used to capture complex biological phenomena. So when I'm working in mathematical modeling in biology to capture biological phenomena, I need to know some effective technique how to model and how to solve those reaction diffusion advection system. For this, we have used operating splitting method. I will explain the operating splitting method. Then for the reaction diffusion part, like for the operating splitting method, we'll break the model into two different parts. One is the reaction diffusion part, one is the advection part. And for the reaction diffusion part, we will use IIF scheme, that is implicit indicating factor method, and its higher dimensional version CIF, that is the compact scheme of its its high dimensional version for solving reaction diffusion part. And then we'll use backward, forward error compensation and correction method with some semi-Lagrangian scheme. In this case particularly we use Courant-Isaacson-Riesz method. I'm sorry. And I'll show you some numerical results that we acquired by solving this reaction diffusion advection system. Some promising result I can show, and then I'll give a summary of the whole exercise, what we did and what is our realization. And last but not the least, we'll discuss some of our ongoing work, ongoing project. Okay, so before we start and get into the mathematical modeling part, I need to give you some idea about the background of the cell signaling thing. So first, background and motivation. So what is cell signaling? Cell signaling is basically how two cells interact between each other. And it is very, very important because this constitutes the complex communication system in any living organism, and it governs all the basic cellular activities like cell differentiation, cell proliferation, and coordinates all the cell action. And any error in this pathway, signaling pathway, can cause serious problem like autoimmunity disease, cancer, this kind of diseases. So this pathway is very important for living organism. So here I will show you some movie that how two cells interact with each other, and there are the two A and alpha 2 cells, and alpha cell maybe secrete some chemical and that will diffuse to the other cell, and you can see here that the receptor of the other cell, the receptor take into the chemical inside the cell, and it will give signal, different signal like what to do. This is the outside situation, what you need to do, whether you need to differentiate the cell or some cellular particular activity, you have to multiply the cell, you have to arrange the cell cycle, whatever. So this is the basically the interaction part of the two cells. Now, when the chemical is around, cells are very intelligent. They try to changes their shape according to their gradient and the chemical reactors. So you can see if it's coming from left, it will change the its shape as well, and this is some experimental result that it really changes. And we'll try to capture the whole phenomena into our mathematical model, this whole phenomena. First we'll start with the basic, this is the complex part of the cell signal. This is the whole part. You can see there is several signal pathway here, but we'll just consider the main pathway. It is called map pathway. We have studied this pathway. Why? There is two reasons. One is this is the most important pathway in the cell signaling. Number two, the collaborators, our collaborators are experimenting with this pathway only. So we have studied this pathway. Although you can have like different pathway in the same cell. This is the cell structure. Okay. So now this is some details of the MAPK cascade, how this works. I'll little bit explain you how this works, and then I will directly jump into our mathematical model. So this is the upstream protein, MAP3K. Now when the input comes, it adds a phosphate group to the protein and it activates. Whenever the phosphate group adds to a protein, that activates the protein. And similarly, you can remove the phosphate group, and this process is called dephosphorylation. This is the upstream protein, that is, this is close to the membrane. Now once this is activated, it will be acting as a stimulant to activate the next layer of protein, MAP2K. So, and for this we have one site to add phosphate group, but the downstream protein has two sites to add phosphate group. So here you can sequentially add one phosphate group here, and then again sequentially add two phosphate group here. So it is totally activated. Now once this is activated, it will act as a stimulant for the next layer of protein. You can see you have added the MAPK one phosphate group and the second phosphate group here, and this will be the stimulant. Once this is activated, this will send signal to the nucleus to do some cell activity. So first, for the first set of model, we'll start with very simple model. And as we get some interesting and promising result, we'll keep on adding complex factor into this model and try to see what happens. So first set of model, we will see this sequential model, this only this part. Then we'll add two layer of protein, that is the cascade model we have done. So first the sequential model. Now, so signaling through MAPK pathway is critical for cellular decision, for as I already mentioned, all the cellular decision. And why our model is novel? It is novel because we have incorporated some special protein, it's called scaffold protein, into our model. And this is the scaffold protein, you can see. And you can see for different concentration of chemical, it uses the same pathway, although it gives send out different output. So scaffold protein enhance the specificity of cell signaling. It prevent improper crosstalk. So it's a practical thing to incorporate into the model. So this is one of the hypothetical situation how we can add scaffold protein into different phosphorylated protein. Like Here you have no phosphate group. P means the two phosphate group. One. So there is just a hypothetical model how many different ways you can add. So now the ultra sensitivity. So what is ultra sensitivity? That for very small change in input, if the output is humongous, is huge, it's called ultra sensitivity. And it has been proved that with addition of scaffold, the ultra sensitivity and bistability, that is the multiple steady state, really enhances. And this is a sequential model. You can see B0 to B1. B0 means no phosphate group added. B1 means one phosphate group added. B2 means two phosphate group added. So on and so forth, up to we consider n phosphate group added. So it has been shown that multi-site phosphorylation, as because you can easily see here we have multi-site phosphorylation can be possible. Multi-site phosphorylation cannot produce Swiss-like response except unnatural condition. So what will be the unnatural condition? Unnatural condition will be the scaffold protein addition. That's what we did in our model. So let's see, can scaffold protein can produce Swiss-like response? So this is we will consider several generic models. So this is one of the model where here the protein is bounded to the scaffold. This is the scaffold bounded complex, and this is the phosphorylation happening into the protein only. Here there is no phosphorylation or dephosphorylation, and this is the addition of the scaffold and dissociation of the scaffold happening here. So I have assumed that we have n phosphorylation site here. So for addition of scaffold, definitely the switch is still very switch-like response is very good. Although without scaffold, you can see from the curve, the switch is not very strong. And moreover, we have realized that for a optimal number of optimal amount of scaffold protein, you can achieve the switch-like response. So this is the some known some result. Then localized kinase, that means here we have changed the position of the phosphorylation. Here the phosphate group is adding when the scaffold is binded to the protein. Now there is two different types of phosphorylation. One is sequential, as I already mentioned. You can add one after another phosphate group, and dephosphorylation can happen as well. And second is the random mechanism. We'll discuss both of the situations. So for the sequential model with scaffold. So this is the model when the phosphorylation is happening in the scaffold bound protein, and dephosphorylation is happening into the protein by itself without the scaffold. So if I consider all the reaction happening on that model, we'll end up with the time derivative. These are, by the way, all the brackets are, these are concentration of the particular protein, and this can be easily modeled with mass action principle. But you can do the modeling with Michaelis-Menten as well as, but we choose to do it by mass action principle. Moreover, we assume the total amount of the protein and total amount of the scaffold is conserved. This is called the conservation law. So if we do some mathematical analysis, so first we set all the time derivative 0, because we are looking here for multiple steady state. We are not interested in single steady state. We are just interested whether we can achieve multiple steady state. And this is important because when people do drug design, they always look for multiple steady states. So it is very practical with respect to the physical problem. So if you set the left hand side 0, and we end up with this kind of expression for the scaffold binded complex and the protein, where all the coefficients are represented in terms of the coefficient of the reactions, all the reactions. I will show you some more. So we have set a pattern, we have found a pattern that for different coefficient, you can write down all the coefficient in terms of the reaction coefficient. So these are all known, all the BIs and AIs. So if I set and do some simplification, we will end up with having a n plus 2 order polynomial here, and ultimately where the coefficient of the polynomial has this kind of trait. Now we have to solve the polynomial and see whether we can have any multiple root of the polynomial. And if we have the multiple root, then our purpose is served. So first start with a simple case when n is equal to 1. For n is equal to 1, if you plug n is equal to 1, we'll get a cubic polynomial, and with some numerical computation and mathematical analysis, we have seen for different set of parameters, we have seen it has only at most it can have one positive root, and we are not interested in one positive root. So we go further. We go further to the case n equals to 2, where you can get the fourth order polynomial, and we randomizely select the parameters here, all the parameters, and see whether we can get some multiple steady state. So we did some two numerical experiment. One, we set the total protein amount fixed and vary the different scaffold amount. And here the A is the stimulant that facilitate the addition of protein. So when you vary the amount of A, you can see for a certain range you can achieve multiple steady state. This is the sigmoidal curve, and this is a very common curve in mathematical biology. So for some range there exists no multiple steady state, but for certain range of scaffold protein, when you vary, you have multiple steady state. Similarly, when I fix the scaffold amount to a fixed amount and vary the protein amount, similarly we can see there is no multiple steady state, although for certain range you can realize multiple steady state. So this is actually a good realization. At least addition of the scaffold protein can get us some multiple steady state. Now we did some stability analysis of the system. We had a system of nonlinear equation. So for general case, we find out the Jacobian like this, and we found some similar structure because the Jacobian is 2n plus 3 order, but we have broken the Jacobian into 9 different components because all the different components had some structure. So we try to find out what is the structure here. But all the Jacobian can be written in terms of the given reaction rates. So you can see all the Jacobian different components had different thing. Now we did some numerical experiment that to see whether which steady state are stable, which are unstable. So this is a very common theory that we try to find out the eigenvalue of the Jacobian and find out whether the real part of the eigenvalue is negative. If all the real part of the eigenvalue are negative, then we have stable node, and if one of them are not negative, then we have unstable node. So for the upper and lower part, as you already know, this and this are stable and this is the unstable. So we have verified with numerical exploration. And this is the second model. We just changed this model to, this was in the previous model, this phosphorylation component was here in the scaffold complex, scaffold bounded complex, and the disphosphorylation was here. So we just switch these two reactions here. Similar, we can capture the whole situation with mass action principle, similar kind of modeling technique, and similar kind of, only this right hand side has changed due to the different reaction. Again, we did some mathematical analysis to see whether we can get some pattern about like for the general case. And for the protein, for the steady state, when you equate the time derivative to 0, so the protein can be written in this form, and all the coefficient again in terms of the known reaction rates, as you can see here. And the scaffold binding protein also can be written as a polynomial of scaffold by itself and the protein here, and these are all known. So again, using the conservation law, we end up with a n+2 order polynomial, and here is the coefficient of the polynomial in different i's. For n is equal to 1, the first experiment, again there is no multiple steady state, so we were not interested at this case. We move on to the next level where n equals to 2, you have a fourth order polynomial, and we, by the way, we use the root function of MATLAB to find out this the roots of the positive root of this system. And the numerical experiment, similar experiment we did where we fixed here, we fixed the total number of scaffold and varied the protein amount. And similarly, for certain range there is no multiple steady state, where for certain range we can realize multiple steady state. And this is when you fix the protein amount and vary the scaffold. So again, for the stability analysis, we try to find any pattern we can have. Again, we find that the whole Jacobian can be written into 9 different components, because each of the components has similar structure, and all the components can be written in the known form of, like, in terms of the reaction rates. So Jacobian can be computed. We try to find out the eigen values of the Jacobian, and we realize the middle one is unstable saddle node, and the upper and lower one is the stable. These are the third generic model, where we shifted both the addition of the phosphate reaction and the dissociation of the phosphate group in the scaffold bounded complex. Here the result modeling technique is the same, but the results are not promising. We end up with a quadratic equation where we have a positive solution and the negative solution. Again, as I mentioned at the very beginning, we're not interested in any single solution. We are, from the very beginning, we're looking for multiple steady state. So this model is not interesting for what we are looking for. For whatever we see for the sequential model, we can see here when the phosphorylation, this reaction and dephosphorylation are placed in a different location, then only you can realize multiple steady state. But if we can place both phosphorylation reaction and dephosphorylation reaction in the same location, then we can never get multiple steady state. This is a good realization. Now we move on to the next level, the more complex cascade model, and we introduce the scaffold protein, and this is the cascade model. So here we consider 2 different proteins where the phosphorylation is happening in the scaffold bounded complex. Here you can see, while A is the upstream protein which is located near to the membrane of the cell, and B is the downstream protein which is located to the middle of the cytoplasm. As you can see, this is the very complex, how all the different ways you can bind the complexes are shown here. Although we can think that this and this reaction are symmetric, but this is not. That makes the model very complicated, because you can see, as I mentioned earlier, you can see E is acting as a stimulant to add phosphate group here for the A protein. But for the B protein, A1, this guy, the upstream phosphorylated protein is acting as a stimulant. So these two reactions are not symmetric. That's why we had like lots of problem. This makes the model more complicated. So, well, this is lots of equation, 13 equation, 13 unknown, and all the reaction component contributes to the nonlinear part here. You can see, but one thing we realized that we can do any mathematical analysis or numerical computation with this many of equation and unknown. So we tried to see whether we can simplify the model with the given, whatever the given conservation law we have. So I did lots of mathematical analysis, and it took me almost like 3-4 months to simplify this. Moreover, before I go and show you some result, these are the 3 conservation law for the cascade model. So first I defined, because I was combining different combination of the equation to see whether I can realize any pattern. So after spending a lot of hours in seeing any pattern, I realized these are the combination of the complex that are coming up in my analysis again and again. So I named them differently so that I can see what is going on. So at the end of the day, we are lucky to realize that all these different combination can be written as 4 basic components: A0, A1, B0, B1. And if I consider the conservation law, you can see conservation law can be written in terms of all these the quantities I have defined. So you have 1, 2, 3, 4 equation, and as because these components are a function of A0, A1, B0, B1, so this will be a 4 equation and 4 unknown. And if I show you the equation, it doesn't look very simple though, but at least we are in a position to do our numerical simulation at this point of time. At least it's better than to handle the 13 equation, 13 unknown. So we did some numerical experiment with that. So I will show you. These are the for A0, A1, B0, B1. Here we vary the total amount of the first protein, that is A, and see what happening. For certain range, you can have multiple steady state. For certain range, there is no multiple steady state or no solution, because if there is no positive solution, you are not interested. We are trying to find out the concentration of the protein. So for the certain range, there is no solution at all. But for certain range, there is one solution. But it is very random. What I realized when I varied for a longer range, it is very random that for certain range we are realizing multiple steady state, certain range there is no solution at all, for certain range there is only one solution or two solutions, because maybe the third solution is negative, so we discard the solution. So again, similarly, we varied the second protein to realize similar observation, although this is little bit consistent here because we don't see much like gap where we don't have any solution. Going to the next, when we vary the scaffold, this is interesting for the value which is lower value, you can see multiple steady state, although the steady states are odd but not very huge number. For certain rays there is no positive solution, but from these things there is random solution, I mean very large number of steady solution. So before I go to that, so this is good in the case that when we solve the sequential model, we realize that for one phosphorylation site, we didn't realize any multiple steady state. But for the cascade model, even for the one phosphorylation site, we have multiple steady state. Now, we only know, we just solved for A0, A1, B0, B1. How to know the other 9? Because we started with 13 components, right? How to know the other 9 components? So we carefully observe that we can find out some linear equation Here U, V, W, all these are known, and A total, B total known. So if I solve this linear system, we can get back all the 13 solutions. So this system will solve the whole system, whole cascade model. Although we simplified to the 4, and now it's time to map it back to the original model. And this is the experimental evidence that scaffold protein always localize close to the membrane. That's what we incorporate into our model. Now this is the special case. I'll go really quick for this. This is the special case for different combination, and you can see here we have mentioned that region with scaffold protein is always close to the membrane, and we can do all these special combination into this mass action principle property. So scaffold protein had definitely an impressive contribution into the model, and there is some simulation you can see when you can do without scaffold, localized scaffold or uniformly distributed scaffold. So, as I already mentioned, there is nothing new I can tell you. The scaffold protein combination can facilitate the switch-like response, and for the sequential model, in order to bistability, phosphorylation and dephosphorylation must take place at different location. And for the cascade, multi-site phosphorylation and scaffold binding in cascade leads to bistability even more robustly than the model without cascade, the sequential model. Okay. Now the second part of my research is that we designed a numerical scheme to handle the reaction diffusion advection system. So this is very commonly used to capture complex biological phenomena. This is the advection part, and this is the reaction diffusion part. And because I'm doing this kind of modeling, I need to know how to solve those models. So this is one part of my training, how to design some effective scheme to handle this kind of system. So what is the problem with reaction diffusion part? Because it's very difficult to solve the reaction diffusion equation, because the reaction rates vary so largely that introduce stiffness into the system. And when you try to solve the system, you need to have very restricted time step size. So for the CFL condition, small time step are required for the CFL condition, and we need to find some method to overcome this complexity. So this is not my work. We implement existing implicit integrating factor method into my work. So this is a very strong, stable scheme to solve reaction diffusion system. First, for the space discretization, we discretize with central difference method, and Then we, this is the formula for the second order scheme. This is under unconditionally stable scheme. And the computation cost is n square and storage cost is n square. It's very, very good. So we'll go to the extension of the compact version of the scheme for higher dimension. But before that, I'll show you some result. I run some numerical simulation that I incorporate into my operating speeding method. So this is the test problem. For RKT method, this is the explicit scheme, and we fix the time step, fix, and see it takes a lots of CPU time. But when you apply the IIF, it can solve. For the RK2, it was 178. For IIF, it can solve significantly lower